Dr. Fleming, when is our next test?
Right now.
Right now?
Yeah, I hope you studied.
How does that work? Oh.
No, we're going to finish up chapter 26 today. And so it's basically getting ready to happen. I'm going to aim for Monday.
Okay.
What's going to happen is when that exam goes live, it's going to have to work a little differently than exams have in the past, just because of the apocalypse. So the way this will play out is I'll post the exam probably either just before or just after Monday's class. You will go in and certain things that I normally do for exams aren't going to happen. For instance, I'm not going to do a drop and double thing because of the nature of online exams, and because I cannot expect you guys to use some of the anti-cheating tools because you may not have the equipment available for them, and you didn't sign up for an online class, so it's not reasonable for me to expect them. Those exams are going to have to be open book.
Ooh, that is a boy. I'm about to kiss you through the computer. I
swear. None of that, because I have to ask different kinds of questions, right? So never get excited about open book exams or take-home exams, because they're a different animal.
They all make corner.
Yeah.
Oh, dang.
Yeah. So don't claim victory yet. It does mean the things you maybe need to spend your study time on might be a little different. You don't have to necessarily memorize every detail of every stupid equation, but it's super important that you be able to be conversant with the ideas, know the big picture stuff, because a lot of the questions are going to be designed to help me pick out the people who really get the stuff from the people who are just trying to look up answers in the middle of the exam. The other thing, time will be a factor. So the exam will be timed. You'll have probably 2 hours from the moment you open it to finish it. So when you sit down, when it goes live, I'll probably give you between 24 and 48 hours to do it, just so you have time to get your situation straight. But once you start it, you don't stop until you're done, because when you click off of it, it's going to end. What will also happen is the questions will end up being from a question bank, so that you're not going to get the same questions as somebody else. This is so that, when Sally boots up her computer, she can't, look over at Kristen and be like, "Hey, Kristen, what'd you get for number one?" Because your number one's not going to be the same as Kristen's number one.
So the test is still online?
Well, it's going to have to be online. It'll be delivered in very similar a fashion to how you guys get your homeworks. Mm-hmm. Except that instead of being one question at a time, it'll be the entire slate. You'll put your answers in, hit submit.
So you know how you give us partial credit for work?
Yeah. Yes. Stop talking and I'll tell you.
Oh, my bad.
It's like I'm just trying to tell you. So what's going to happen is you'll put in your answers like you would for a homework. But unlike the homework, most of your points aren't going to come from the final answer. So what will happen is there'll be a separate assignment, a separate link. So after you've turned in your answers, you're going to have to upload your work in a file that I can read. That's how that, you can always take snapshots of the paper and upload them. That needs to be done reasonably close to when you finish the exam. If I notice that you did the exam and then 3 hours later you turn in your work, that's going to be a no-no. Just because I'm trying to capture your work during that time frame. Does that make sense?
Yeah, so will you have it set up to where we'll be able to take a picture on our phone and upload it, or?
Well, the same way you would a pre-lab or any of the other kind of assignments you turned in that way.
Right. Okay.
So, however you've done that in cases of pre-labs and that kind of stuff, you'll do the same process. You'll upload your work there, and I'll have to be able to give partial credit based on that. So make sure I can read it, right? Make sure it's legible. and turn that in promptly after you finish the exam, and that's where your partial credit points will come from. Not an ideal solution, but we're working with what we got, so that's how it's going to happen. Does that make sense?
Yeah.
So quick question, Dr. Fleming. I think I missed the time for the exam. Now you said you're actually going to open it a few days early, and we'll start working it.
Yeah, like unlike a regular exam where you all sit down at one time and take the exam, there's no reason to do that in an online class. So what I'm going to do is when the exam goes live, you'll have, probably either 24 or 48 hours to start the exam, right? But once you start the exam, that's going to start a clock, and you've got, X number of hours, probably 2 hours to finish, and turn that in. Does that make sense?
It does, but is there any way like you could give us like a lot of time there, just because of what's going on,
That's why I'm giving you like a couple of days to do the exam. But as far as doing taking the exam, the act of taking the exam, I have to time limit that, because what I can't do is leave it super open-ended, because then what's going to happen is you guys have way more time to Google stuff. You have way more time to look stuff up. And I'm not testing your ability to Google things. I'm testing your ability to know some physics. So that's kind of my compromise for having open book stuff, is that if you're super reliant on the open book stuff, it's going to slow you down and you're not going to get as much done.
But is it still the same amount of questions?
The number of questions will be slightly different. Again, I'm having to change the nature of some of the questions. So what will happen is there may be like more than just 4 big questions. There may be lots of smaller questions. And some of those questions may be open-ended, where I'm not just wanting you to plug numbers into an equation. I'm going to want you to explain a bit more. And again, this is to help me sort of differentiate between the students who get the stuff and the students who are just parroting what they're reading online. Does that make sense? I'm trying to make the Chegg factor less of a factor.
And then when is the test again? I wasn't here when you said it.
So what's gonna happen is the test is gonna go. I know I was like, oh my god, the test is gonna go live probably on Monday. And so what will happen is once the test goes live, you're going to have either 24 or 48 hours in order to start the exam.
Yeah, I got that. I got that part. I got that.
Okay.
I just didn't know what day.
Okay. But that's the time frame that we're looking at. It's going to cover chapters 24, 25, and 26.
Is there extra credit?
Will there be extra credit? I don't plan on there being extra credit.
Okay.
But that's how that's going to play out. So we'll look to see how that works, and hopefully.
So all the homework is due Monday.
That is a correct statement. Yes, a week from today, the homework should be due. Yes.
We learning anything new today with the test, or
yes, we're going to finish up chapter 26.
Oh, all right.
Yeah, it should be a short day. The chapter 27 homework, I'll post it sometime this week, and we'll start doing chapter 27 stuff later on this week. Our lab this week is actually a chapter 27 lab, but we're not ready for that yet. But what I want to do today is just sort of knock out the rest of chapter 25 and 26, which is about optical instruments and some stuff like that. So any other questions about the exam before we
actually, it's not related to the exam. It's related to the homework. So just to now bombard our minds, is there any way you could just leave out 27 for now until the test is done?
27 is not going to be on the exam, and I haven't posted the chapter 27 homework yet.
Okay, just having it on there, 27 kind of, can become a bit mind-bothering because, you're looking at it like.
Well, that will not be, the Chapter 27 homework will not be due on Monday.
Okay.
So, yeah, it will go live sometime later this week. Translation, when I finish it. But and I don't expect you to spend time starting it until after the exam. But as of right now, the only ones that have been published have been the chapters 24, 25, and 26. So the homeworks that have been published are the ones that will be due. Anything that publishes after this moment will not be due on Monday. Does that make sense?
Yes.
Yeah, that makes sense.
Okay, cool.
Let's get started. Oh, no.
While I'm thinking about stuff, just a reminder, if you're planning on doing the credit or no credit grading option, I've only had like one student like come forward on that, which I guess is cool. Maybe they're confident. But if that's the thing you plan on doing, remember there is a definitive deadline for that. It is the 29th of April, and you have to do it in writing. So if you're thinking about making that choice, by all means do it, but don't let that slip you by, because I can't wait until the end and say, oh, so and so's failing, I'll go with no credit for them for their GPA, because by then it will be too late.
Isn't we could actually explain that a little bit, because I did
Extend crazy.
Like how the credit no credit thing works.
Yes, please.
Okay, so the way it works is, between now and the 29th, you will have to submit to me in writing a request that rather than give you a traditional letter grade, A, B, C, D, E, or F, instead of giving you a traditional letter grade, I will give you either just a credit or no credit. And that's all you're going to get on your grade report from me is credit or no credit. Now, if you don't opt to take that deal, you'll get a regular grade like you would any other semester. It's going to count towards your GPA and all that stuff. Yay. If you take the credit or no credit thing, if you send me the request and I respond in writing before the 29th, what will happen is when I get to the end of the semester, I will look at your final grade. And if your final grade is sufficiently high that I would normally have awarded you a sufficiently high grade that you would go on that it would count toward your degree, basically, you're going to get P. It's going to say P for pass on your grade report. It won't say whether it's an A, B, or a C. They're all going to be the same. If you would have gotten a D or an F, which would have required you to repeat this course, since everyone who's in it has to have a C or better to graduate. Whoever's like making all that noise, could you please mute yourself, please? But if you've got a D or an F at the end of the semester, I will, I'll give you it'll say no credit on your exam, your final grade sheet. You'll still have to repeat the course. I mean, it's still a fail, but the advantage of this is that will not affect your grade point average, right? So if you're worried about you're screwing up your GPA and ending up on sanctions, that shouldn't happen, right? It's going to be like it'll be like the class never happened. But that's the idea, and it's there in case your grade might have been negatively impacted by the coronavirus and this weird disruption. So there's some students who may have been cruising for an A and they're going to end up with a C, but they don't want to have a C on their record. So they'd get a P. It won't affect their GPA. They can still move on to the next class, so it doesn't cause them to repeat or anything like that. But it avoids the issue of having a crummy grade. And if you've got a failing grade, it allows you to basically walk away from the class without taking the GPA hit. So
gotcha.
That's how that works.
Okay.
So yeah, depends on what your situation is as to whether or not that's something you want to do. But it is an option that you should be aware of. A lot of other schools have done the same thing, just because of the extraordinary disruption to your normal working scheme that you've had to endure with this pandemic. So that's where we're at. All right, guys. So what we're going to do today is we're going to finish up chapter 26. We talked about vision correction the other day. We learned about different varieties of vision maladies and ways in which they can be corrected. And there's a couple of other things that they talk about in chapter 26. They have a section on color vision, which is kind of where biology and physics sort of intertwine a little bit. So we'll talk a little bit about that to make sure you're aware of how that works. They talk a little bit about optical instruments. So we'll talk about microscopes and telescopes, and you guys are probably going to be particularly interested in microscopes. So you'll have at least some sense of what you're looking for the next time you're stocking a lab and you're trying to figure out what microscopes you need. You'll have a better sense of what it is that makes a microscope appropriate. And then we'll talk about what they call aberrations, or places where a lens may distort an image and cause the image to not quite work effectively. And then there's one last issue that was actually in chapter 25 that we need to talk about today, and that's how do I deal with mirrors? We've talked about lenses, but we haven't talked at all about mirrors. And even though it's in chapter 25, I tend to save it for last simply because they don't really add a whole lot of extra new stuff to the situation. Mirrors are super, super simple. And once you have a handle on how lenses work, adding mirrors in is trivially easy. But that's my plan for today. I suspect we'll get done relatively quick, so it won't be a full 2 hours. Yay. And then we'll come back on Wednesday, and on Wednesday we'll do chapter 27 stuff where we talk about wave optics. But good news, the end is in sight. You are almost through everything we need to do, and that's a pretty good sign.
How long into the end of the semester?
What's that?
When does this semester end?
Finals week is the first week of May. So
Dang, that's like 2 weeks away.
yeah. Oh yeah. The end is we are coming in on the end. So we're pretty close to on schedule. We've got a little extra time actually, which is nice. But normally if we were this far ahead of schedule, I'd be like, hey, let's do relativity. But you don't want to do that. So we're not going to do that. All right, so let's talk about mirrors first. Let's finish off the last thing in chapter 25 that we didn't talk about. So when we talked about how to deal with lenses, it was pretty straightforward, right? We had what we called the thin lens equation. What was the thin lens equation? No, that's not the right camera, stupid.
That's the 1F equals 1 over I
plus 1 over O.
That's it. 1 over F is equal to 1 over I plus 1 over O. And it's just how we find image formation locations for a set of lenses. F is what?
Our side?
Focal length. Yeah.
Yeah,
focal
your
length,
focal
sorry.
length. Yeah. F is the focal length. Now, what does the focal length even mean? Can somebody explain that to me?
It's from
It's from the lens to the focal point.
yeah.
Right. So if you've got a lens, and I'm going to draw a converging lens right now. If you've got a lens, what's going to happen is if you have a bunch of rays of light come in and be incident on that lens, what's going to happen is they're going to bend. But the light that hits the edge of the lens is going to have a very large angle of incidence, and it's going to bend a lot. The light that hits over here is going to bend a lot. But the stuff that hits near the middle of the lens is going to have a shallower angle of incidence, and as a consequence, it's not going to bend as much. So what happens is, if you send parallel rays of light in, when they come out the other side of the lens, they tend to converge at a spot that we call the focal point. And the distance from the lens to the focal point is the focal length. F. That's the idea. And of course, there are two kinds of lenses. There are converging lenses that cause parallel rays of light to come together, and there are also diverging lenses. There, if I've got parallel rays of light, they're going to bend the other direction, and as a consequence, the light rays will diverge or spread apart. But even a diverging lens can have a focal length, because if you sort of trace those rays of light backwards, if I could draw a straight line to save my life, it is as if those rays of light are diverging from a single spot, and that single spot that the rays seem like they're diverging from is the focal point, and that distance is the focal length, the same kind of way. So we saw that last week, and there was a sign convention for focal lengths, right? For converging lenses, the focal length is positive, but for a diverging lens, that focal length is
Negative.
negative. Yeah. All right. All right. So that was pretty straightforward. But you can also collect and create images with mirrors, right? If you put your makeup on in the morning, looking in a mirror, you're looking at an image of yourself. So clearly, we need to be able to talk about the same sort of thing with mirrors as well as with lenses. And here's the good news. When you're talking about how images are going to form with a mirror, you're still going to use the thin lens equation. It works just as well for mirrors as it does for lenses. The difference, however, has to do with the sign conventions and what those sign conventions are going to mean. So with a lens, if I have a lens that is fat in the middle and narrow at the edges, that's a converging lens. But what if I have a mirror that is round like that, what they call a convex mirror? Now what's going to happen is mirrors don't refract light like a lens does. Mirrors reflect light. And the law of reflection says the angle of reflection is the same as the angle of incidence. So what's going to happen is here's this ray of light coming in and hitting this mirror. Now the normal to that mirror is right like this. So this ray of light is going to hit at that location, and it's going to bounce away at the same angle on the other side. Now down here, parallel ray is going to have a normal that looks like this. It's going to bounce away and hit the other side. Now, near the middle, the angle of incidence is going to be shallower. If I hit it dead on in the middle, it's going to come in and then bounce right back out again, the same way it came in. And so what's going to happen is this convex mirror is going to cause the light to diverge. It's spreading apart. And as a consequence, if I were to imagine I could draw well, if you were to sort of trace these lines, it seems as if the light is coming from a spot that's somewhere behind the mirror. So this would be the focal point of a mirror. And you could also define a focal length the same kind of way. Now, for mirrors, a diverging mirror has a negative focal length. Notice that the focal point is behind the mirror in this case. So far, so good? Also notice there's a relationship between whether something's diverging or converging. The shape of this mirror is similar to the shape of this lens, but a convex lens or a convex mirror, well, one of them is converging, the other is diverging. So be careful. You know, convex lenses have positive focal lengths. Convex mirrors have negative focal lengths. That's super easy to get confused with, which is why it's probably better to remember that diverging lenses and diverging mirrors are both negative. Diverging means negative, converging is going to mean positive. Now, what would a converging mirror look like? Well, a converging mirror would be concave, right? So imagine this is my shiny surface, and what's going to happen is because it's bowed inward, a light that hits here is going to bounce like so. Light that comes in and hits down here is going to bounce like so. Light that goes and hits right in the middle is going to bounce and come back the way it came. And there's going to be a spot where all those light rays tend to converge. That, of course, is my focal point. And that, of course, is my focal length. For a converging mirror, F is positive. So if you could just remember, converging is always positive, diverging is always negative, regardless of whether you're talking about mirrors or lenses, that will always be true. And all that's tricky here is that diverging mirrors are convex and converging mirrors are concave, whereas for lenses, it's the other way around. Converging lenses are convex and diverging lenses are concave. Right, super easy so far?
Yeah.
Now, let's talk about images for a second. Let's do a quick image problem. All right. Let's imagine that I've got a diverging mirror. Again, that's one of those convex mirrors, kind of like the ones they put up in the corners of like convenience stores to help the guy behind the counter tell if people are stealing beer. You know what I'm talking about?
Yeah.
Yeah. It's like one of those. Now, this diverging mirror, let's give it a focal length of 20 centimeters. And I'm going to have an object, and I'm going to place that 30 centimeters in front of the mirror. I want to find where the image will form. So when I go to figure out where the image will form, I use the thin lens equation, just like we've been doing. And which of those things do we know?
F and
what is F?
20.
And
Negative 20.
Negative 20, right? Why? Because this is 20, but it's diverging, right? And, you know, especially on questions, I'm a jerk. I'm never going to say it's got a focal length of negative 20. I'm going to tell you it's a diverging mirror with a focal length of 20, and I'm expecting you to know that you have to make that negative. So this is 1 over 20. And I want to figure out where the image is going to form. So I'm solving for I. And of course, the object distance was given to be 30. So I move this over. I've got negative 1 over 20 minus 1 over 30. And that's going to equal 1 over I. And of course, what's that going to be? Well, that's going to be 3 over 6, or 3 over 60. That's 2 over 60. So it's going to be negative 5 over 60. So when I flip it, I is going to equal negative 12 centimeters. So what I've got to do is figure out what does that mean. Now, when we were dealing with lenses, what did it mean if I got a negative image distance? It's a virtual image. And that is still going to be true even with mirrors. If you get a positive value for your image distance, it is a real image. If you get a negative value, it's a virtual image. Now, what's different is how you interpret what that means for my picture. If I had a lens that created a virtual image, right? A virtual image would appear on the same side of the lens that the light was coming from. So if my light was coming in from the left, as it is here, and I had a virtual image being formed by this, that would be an image that was occurring somewhere on the left side of the lens. For mirrors, though, it's the other way around. A mirror is going to generate an image that is virtual, and it will appear behind the mirror. Does that make sense?
So it's the reverse of the lenses.
Yes. For lenses, virtual images appear on the same side of the lens as the real object. For mirrors, virtual images appear on the opposite side of the mirror. So like when you stare at yourself in the morning, when you're doing your makeup, you are looking at a virtual image of yourself because it appears there's another you standing behind the mirror. Does that make sense? All right. So, the fact that I got a negative image distance means I've got a little version of this dude who appears behind the mirror. Now, what's the magnification? Same formula as before. M is equal to negative I over O. So notice what's going to happen is it's going to be negative 12 over 30. So that's 1.25, 6/5. So what's going to happen is this mirror has magnified it. I'm going to see an oversized version of myself behind the mirror. Notice the magnification is, I smeared it, that's gross. I smeared it, I got a positive magnification, which means my image is upright, which still, it tracks with what you've typically seen with mirrors. When you stare at yourself in the mirror in the bathroom, you tend to see an upright version of yourself, right? Super easy.
Can M be negative?
Could M be negative? Absolutely. You could certainly end up with an inverted image, and it's unfortunate that I have I have a big convex and a concave mirror that are like in the lab that I usually pull out for you guys to play with during this lecture if we were in regular class. I don't have an equivalent of that, or I'd show you sort of like what's happening. But if you were to take a convex mirror, so here's a mirror that's curved the other direction, right? And imagine that I gave this guy the same focal length as I did the other guy, except now I've got my object 30 centimeters in front, and I solve that problem, right? So all that's changing is that this is no longer negative, right?
Mm-hmm.
So now I've got 1 over 20, 1 over I plus 1 over 30. When I move that over, 1 over 20 is going to be bigger than 1 over 30. So when I solve that, I end up getting my image distance to be 60 centimeters, but it's positive 60 centimeters. All right, you guys buy that? So what's going to happen is I'm going to get an image of this guy behind him off the screen somewhere. There we go. And what's the magnification going to be? Oh, sorry. It's going to happen to be, when I do M, it's going to be negative I over O, but that's going to be negative 60 over 30. So that's negative 2, so it's going to be twice as big, but upside down. And you can kind of see why that is if you could trace rays better than me. Let's do it off to the side here. Maybe I can pull this off. So, like, here's my original dude, right? And I'm going to draw the 3 principal rays, and I'm going to try to do this well. So here's the focal point. The first ray comes in parallel, it bounces out, and goes through the focal point. The other one is going to hit right here and bounce right there. And then the third one goes through here and out there. And you can see I drew this one poorly. They should intersect somewhere back here, but now you can see why it's upside down.
Mm-hmm.
Does that make sense?
Yeah.
I've always sucked at doing these drawings, which is why I hate doing these lectures. But conceptually, that's what's happening, is that the light's going to end up converging, but it's going to take a while to get there, and they're all going to converge down here, so the guy's going to be inverted. But it will be a real image because the light really does supposedly all converge at that spot. So with real images, for lenses, the real images appear on the opposite side of the lens. But for mirrors, real images are going to appear on this same side of the lens as the object does. That's pretty cool. Also remember that with real images, you can actually project this onto a screen, whereas with a virtual image, you can't, right? You're never going to take that image of yourself in a mirror and project that somewhere. It's going to always appear like somebody's floating behind the mirror. But here, I could actually project that into real space. You may have seen it like lying around the physics lab, but I have that little black bowl that has like a mirror on the inside. And there's a little object inside it, and it creates kind of like this weird hologram image at the top. That hologram type image is the real image formed by the mirrors inside the bowl. So sometimes real images will actually appear to look sort of like little holograms. They're really cool. All right, so far so good. You guys can do this?
Mm-hmm.
So that's all there is to it. And quite a lot of optical instruments rely on some combination of mirrors or lenses. And all you have to do is remember the sign conventions, and they're super easy to deal with. Let's talk about optical instruments for a second. Generally speaking, optical instruments are just combinations of lenses. For instance, telescopes are easy. Right. In general, what's going to happen is a telescope consists of 2 or more lenses, but the simplest ones consist of 2 lenses separated by some sort of barrel distance. And what generally will happen is the length of the telescope is generally chosen to be very, very close to the sum of the focal lengths. So if this right here is f1 and this right here is f2, the sum of these 2 distances is very close to that length. And so what's going to happen is you're looking at some very, very far away object, like a planet, maybe it's Saturn. And what's going to happen is your first lens is going to generate an image of Saturn at some point. It's going to be a real image, so it's going to happen somewhere to the right of this lens. And conveniently, right, when you go to do the work here, well, what's going to happen is you're generally looking at an object that is super, super far away, which means your object distance tends to be something huge. Let's assume that for the sake of argument, your object distance is like infinity. If this is like infinity, this is going to be basically 0. But that means that you're going to end up with an image that's going to be very, very close to your focal point. So you're going to get a little tiny image of Saturn right there inside your telescope. And then the eyepiece will then resolve an image. And typically what will happen is these two distances will be just a smidge inside. So in other words, this plus this will be a little bit smaller than this. So you won't quite be exactly at your focal length. You'll be a little bit inside this one. And when that happens, what's going to happen is you'll create a virtual image of of planet Saturn for this lens. And so the second image will be somewhere a little bit further back. And what's going to happen is I could just use this as the object for the second lens. And we did that problem last time. So far, so good?
Mm-hmm.
Now, here's what's a little bit tricky. When you go to work through the magnification of the planet that you're looking at, what you're generally going to find is that your magnification is probably going to end up being smaller than 1. And you might think, well, why on earth would I want to use a telescope if it doesn't make the object bigger? I want to make things bigger, right? Well, it turns out that you don't necessarily need to make the object bigger, because think about it. If you're looking at the planet Saturn is huge. It's several hundred times larger than our planet. So I wouldn't want to look at an actual size image of the planet Saturn, because it would be like looking at an actual size image of the planet Earth. You're only going to make out a tiny little smidge of it. So having a magnification of less than 1 is not that big a deal. What you're trading off, however, is, yeah, this picture, this little image of Saturn is super, super tiny, but it's also really, really close, so it's easier to look at. Does that make sense?
Yeah.
Yeah.
So the absolute magnification is not what you need. You need something else. And the thing that you need is something they call angular magnification. And angular magnification is a pretty straightforward concept. Generally, they'll use little m for the total magnification and capital M for the angular magnification. So little m might be, the height of the object over, or the height of the image over the height of the object. The angular magnification is about what angle it makes when you look at it. So for instance, if you've got an object that you're looking at, and here is your eye, that object is going to subtend a certain angle. In other words, it's going to take up a space in your field of vision of a certain number of degrees. Does that make sense?
Yeah.
So I'm going to call that angle theta. But then let's say that I create another version of this, an image of this somewhere closer to me. Well, even if that image were the same size, the angle that it subtends could be larger. So we're going to call that angle theta prime. So theta prime is the angle subtended by the image of the object, and theta without a prime is the angle subtended by the original object. Now, if I'm looking at like an object like a planet, this is the angle that it makes when I look at it with my naked eye. And if I'm looking at, say, the planet Saturn with my naked eye, what does it look like?
A regular star.
Speck. It's a tiny little speck. It looks like a star, right? So what angle does it subtend? Hardly anything.
Right.
But through the lens of the telescope, I can make it subtend a much larger angle. So it appears at least bigger to me. I can make out more details when I have it subtend that larger angle than I could when it was a speck. So even though the image is technically smaller than the actual planet, that's not what matters. It takes up more space in my field of view. And so the angular magnification is just the ratio of theta prime to the original theta. And that's the thing that I'm looking at when I go buy a telescope. I want to have something with a large angular magnification, even if the absolute magnification is not exceptionally large. Now, it turns out that the angular magnification you're going to get is going to be related to the focal lengths of the lenses that you use in order to do this. And I'm not going to derive it because I can't do the geometry, but it turns out that it's just the ratio of the two focal lengths. FO is the focal length of your objective lens. The objective lens is this one, right? This is the one that you're pointing at whatever you're trying to see. FE is the focal length of the eyepiece. So this is the one you look through. So if you're looking for the angular magnification, all you need to know are the focal lengths of your objective lens and your eyepiece. And it's super easy. And it's possible even to have a telescope that uses not just two lenses, but two mirrors, or a mirror and a lens. Let me see if I can show you a picture that doesn't look like it was drawn by a third grader. All right, so you can see here is a design straight out of your textbook of your typical refracting telescope. And again, what's happening is you're looking at an object that is super, super far away. So your objective lens is first collimating your original light, and it's creating an image somewhere in between your objective and your eyepiece. Now, this is a cool 3-lens telescope rather than a 2-lens telescope. And you can see that what's happening in the middle here is what they call an erecting lens. And all the erected lens is doing is it's creating a second image of the first image with a magnification that's usually not especially big, but conveniently it inverts. So whereas here's my original image upside down, the second image is right side up. So now when I'm looking through my eyepiece, what I end up seeing is the image from the eyepiece is this final image, which is a virtual image created by the third lens of the image from the second lens, which itself was an image of the first image from the first lens. Right? So that's how you make a telescope that I can look through at terrestrial objects and not see them be upside down. Here's another example. This is a lot of astronomical telescopes will use this design, where what happens is you've got a very large concave mirror. So you'll have a big fat barrel with a huge, huge lens. That's super helpful when looking at objects in the night sky, because the bigger your objective lens is, the more light that it can let in. And that's going to be important because if you don't let in much light, your image is going to be super, super faint. And even if you magnify it, it's going to be hard to see. And so what happens is this mirror generates an image, and all this is here is a little collimating mirror that helps deflect it out to the side. So these reflecting telescopes like this tend to have an eyepiece that's not behind the barrel, like, you know, the ones you hold up in your hands, but instead, here's this long cylindrical barrel, and there's an eyepiece that you look in through the side. And all they're doing here is just using a mirror to divert the image so that you can point your eyepiece at the side. So you would still do the same sort of thing. You could find the angular magnification of this particular telescope the same way you would otherwise. It's still going to be the ratio of this focal length to this focal length. Super easy?
Mm-hmm.
So, yay, telescopes. Telescopes are cool. What about microscopes? You guys are going to care more about microscopes than you would about telescopes. And there's a couple cool diagrams of those as well. And a couple of things that I want to point out about microscopes. Microscopes designs are similar to telescopes in that they tend to consist of an objective and an eyepiece separated by some small distance. And again, you'll notice that my barrel length, the length from one lens to the other, is usually pretty close to the sum of the two focal lengths. You'll notice here that the sum of the two focal lengths is a little bit smaller than the barrel distance. And so what's going to happen is, here's your slide, there's your sample. Your objective lens is the one at the bottom near your slide. Your eyepiece is the one that you're actually looking through. And what you'll be seeing is a virtual image caused by the first image created by the objective lens of your initial sample. So mechanically, and in terms of how you would do the math, microscopes and telescopes are exactly the same. All that really gets changed are what kinds of lenses you typically use and the various placements of the lenses relative to one another. What happens is, when you go to look through this lens here, you're utilizing your own eye and you have a near point where you can't converge or you can't focus on images within a certain distance. And so what will happen is you can change the barrel length of your microscope by turning the dial. That's going to allow the image to form at a location that is beyond your near point. And at that point, that image will appear to be in focus for you. Right. But other than that, there's nothing here that we can't do with the same sort of mechanisms we've done with telescopes and other two-lens compound objects. There is something that I do want you to be aware of, and that is about light collimation. Again, your total magnification is just the sum of your two multiplications. That's true for any two-lens system. But what I'm going to point out in particular is something called your numerical aperture, or more probably familiar to you if you're into photography at all, your F number. So here's an issue that you're going to have. And so here's your lens, and here's the sample that you're looking at. Now, what's going to happen is you're going to have rays of light leave that sample in every possible direction, right? So I'm going to have rays of light leave that sample going over here, leave that sample going over here. But what's going to happen is none of these rays of light are going to hit my lens, right? Only rays of light that leave within this angular space are going to hit my lens and go on to form my image. And the amount of light that you get in your lens is going to determine how easy a time you have seeing it, right? If you don't get much light, your image will be faint if it forms. So increasing the amount of light capture you get is going to be a super critical issue for microscope design. And so the numerical aperture is just a way of designating how much light capturing can your microscope do. And the way they do that is they talk about your acceptance angle, theta. So theta is your acceptance angle. That's this total angle here. You cut that in half, and you call that angle alpha. That's the alpha here. And what's going to happen is your numerical aperture is going to depend on what that angle is, and also the index of refraction of your lens. Because the more your light bends, or the bigger your index of refraction, the more light you can bend into your field of view. Does that make sense? So, super easy. So, basically, if you get a larger numerical aperture, you're going to be able to make out more detail with your lens than you would with a smaller numerical aperture. Now, how do you get a larger numerical aperture? There's two ways. One is you could change what they call your working distance, the distance from your slide to the lens, right? You change that, you're going to get a wider angle. The second thing you can change is the size of your objective, right? If your objective took up more space, it's going to collect more light. But there's a third way, and this way is kind of cool because at some point this becomes impractical. And that's where oil immersion microscopes become helpful. We have several of them in the department. So what an oil immersion microscope does is you use an immersion layer where you've got an index of refraction that is larger than 1. And so what's going to happen is, you know, here's my cover glass. I've got light coming from my sample through the cover glass, but then it's going to leave. And what's going to happen is they've plotted out the paths that light rays could take through various media. Imagine I didn't have this oil immersion layer here and all I had was air. Well, air has an index of refraction of 1. So what's going to happen is light's going to refract out. It's going to refract out a lot. And it's going to bend away from the normal. I'm trying to notate and it's not working because I'm stupid. There we go. It's going to refract away from the normal a lot. And as a consequence, there's going to be a lot of light that doesn't get to your lens. However, if you use this oil immersion layer between your cover glass and your lens, what's going to happen is that's going to have a higher index of refraction. Typical oil is 1.51. That's almost the same as glass. And as a consequence, your light's going to refract a different amount, and you're basically increasing the angle through which light can emerge from your cover glass and still make it into your lens. So what the oil immersion is doing is it's helping you collect more light from your sample and therefore have a brighter and more detailed microscope image just by ensuring that you're not losing more light as it refracts out of your cover glass. So when it comes to quantifying this stuff, sometimes they'll refer to what they call an F number. And if you've done any photography, you might have heard of f-stops. So an f-stop is basically this. But the F number is basically just the ratio of your focal length to the diameter of your lens. And remember, changing the diameter of your lens can change your acceptance angle. And that's going to be the relationship between your F number and your numerical aperture. This shouldn't come up much, but if you do any sort of microbiology where you care about microscopy, you might be buying microscopes, and knowing the numerical aperture of your microscope might be helpful. Again, bigger numbers are better than smaller numbers, but that's all it's doing is it's changing how much light you can collect from the sample. Super easy?
So far.
Yeah. So in terms of optical images or optical devices, that's the thing that I need you to be able to follow. The other thing that I want you guys to be able to wrap your heads around are sources of aberration. I'm going to die a little inside when I ask this, but how many of you guys saw the J.J. Abrams Star Trek movies?
I didn't see any of them.
Who?
Yeah. You guys, you're making me so sad right now.
I did.
Nobody watches movies. It's terrible.
I watched it.
You don't watch nerd movies. That's the problem. All right. So, if you watch the J.J. Abrams Star Trek movies, one of the things that he, as a director, is super, super interested in is something called lens flare, right? And a lot of the special effects, even though they're CGI effects, what he would do is he would create, because he thought they looked pretty, like lens flares in the camera. So I'm going to show you kind of an example of what I mean by a lens flare. But lens flares are just one example of what we call image aberration. So you can see here that what we've got is somebody's taken some sort of picture of like a sunrise, but what's happening is you're getting extra refractions in your lens, And you get these like weird, funky sparkle patterns. Right, that is lens flare. And those are one example of image aberration, right? And, you know, again, it's one of those things that sometimes you want to avoid that because it's messing up your picture. Other times, photographers might actually use it because I think it makes it look pretty. But lens flare is an example of inadvertent behavior that you're getting in your lens because of limitations in our ability to craft those lenses. And it's not the only example of aberration, but it's useful to point out a couple of things. One, notice how this lens flare has like little circles of different color, like some are blue, some are red, some are green. So what I'm getting is images forming, but I'm getting images forming in different places depending on the wavelength of my light, right? That factor where you start to get blur in your image because of different wavelengths is called chromatic aberration. See if I can find an example of chromatic aberration in a photograph. So you can see that what's happening, this is a pretty good way of seeing how it works. So what's happening is you're taking an image with largely white light. But remember, glass is dispersive, right? You did the lab last week where you had to calculate the Abbe number for the things in the simulation. And that Abbe number was a measure of how dispersive your media was. It was a measure of how different the index of refraction was for some wavelengths compared to others. In general, shorter wavelengths like blue light are going to end up refracting a lot more strongly than longer wavelengths like red light. So you can see that in this image here, all the wavelengths come in together, but what's going to happen is the blues, they refract a bunch and they have a focal point over here, but the reds don't refract nearly as much. Their focal point is further back there. And so what would happen is if I was forming an image using this lens, I'm going to get a blue image in one location, but a red image in a slightly different location. And what that's going to show up for show up like in my picture, and I'm not sure if you can make out the details, but like you can see, can you see here at the border? It's most noticeable at the boundary. But I'm not sure how well it shows up. See that kind of like weird glowy blur right here at the edges? That's chromatic aberration, right? It's because you don't notice it so much in the middle because all your colors are kind of mixed up. But what's going to happen is there's a region out here at the edge where you're only getting one set of wavelengths, and it causes a kind of a weird blurriness of your images. But it's a kind of a rainbow blur. That's chromatic aberration. Now, what does chromatic aberration come from? It comes from having different moments or different amounts of refraction in your lens. If I wanted to correct for chromatic aberration, how would I do it? I hear somebody typing. How would I correct for chromatic aberration?
Should we change the lens?
Yeah, the type of lens will help you do that. Because remember, chromatic aberration is happening because you're using a lens that is dispersive, right? So what you need is you need to have a material that doesn't have much difference between the index of refraction for red light as it does for blue light. And again, going back to the lab last week, that was like the difference between flint glass and crown glass. One of those was highly dispersive, right? If it was highly dispersive, that means that the index of refraction was, or the Abbe number was quite small. And that means that you had a huge difference between the long wavelength refraction and the short wavelength refraction. If you had a really huge Abbe number, or something bigger than 55, it doesn't disperse as much. And as a consequence, you get less chromatic aberration. So that's one kind of aberration. The next kind of aberration I can probably make some sense with if I draw you a picture. And that's called spherical aberration. And spherical aberration is going to happen because, you know, when we draw these lenses, we imagine these lenses are probably going to have some radius of curvature, not unlike a sphere. And what's going to happen is, as long as I don't get too close to the edges, you know, all the light's going to refract in such a way that it's going to focus at a point. But what's going to happen is, out here at the edges, you start to get very, very rapid changes in the angle from your angle of incidence. And as a consequence, it's very, very hard to get the curvature just right at the edges. And what's going to happen is, sometimes that light doesn't quite focus as well. You get that light converging somewhere other than where the main focus is, right? So spherical aberration which I have just proceeded to on camera misspell because there's only one B and two R's. Double letters freak me out. So spherical aberration happens because of light focusing poorly at the edges of the lens. So the way you're going to combat spherical aberration is you're just not going to use that light. Instead, what you'll do is you'll put in like a blocker. And what's going to happen is, this is often called an f-stop. And what's going to happen is, light that goes through the edges of the lens, it's going to have to hit this little blocker. It can't get through. And only light that goes through this small aperture is going to actually make it through. The light that gets through the aperture is the stuff that hit towards the middle of the lens, which is not going to be subject to spherical aberration. Now, there is a trade-off, because what am I doing when I use that f-stop? I'm decreasing the angle of acceptance of my lens. I am effectively making my lens smaller and take up less space, which means I'm collecting less light. So if you're worried about collecting a lot of light so you can make out detail, sometimes there's a trade-off between reducing spherical aberration and the blurriness you get from the stuff at the edges and the amount of light you can collect. Sometimes spherical aberration actually works for you. One B, stupid. So again, people who can draw pictures way better than me. There we go. So you can see that what's happening is that's not as good a picture as I thought it was. There we go. That's a better picture. So you can see that what we're looking at here is the performance that I want from my lens is like this top picture, where the stuff that hits the outside edge all focuses at the same spot. But what's going to happen is, here, the stuff that hits the outside edge, in this case, it's deflecting too much. It's converging too soon. whereas the stuff that goes through the middle is converging further back here. And so you end up with, different parts of your lens trying to create images at different locations. And what's that going to look like? Well, you get weird distortions and blurriness. Why might that matter? Well, a couple of places. One is depth of field. So here's a good example. So take a look at these two pictures. All right. What's the difference between those two pictures, aside from the slight change in her expression?
It's not blurring the second one, the back.
Aha. Yeah, what's going to happen is in the first image, you've got a pretty clear view of the lady in the foreground. But what's going to happen is in the background, it's blurry as all get out. Now, for a photographer, sometimes that's what you want, because if you're the photographer, a lot of times you want to draw attention to certain elements of your picture. In this case, he wants you to be paying attention to the lady in the front and not all the trees in the background. Whereas over here in the second picture, what's going to happen is not only is she in focus, but all of the stuff in the background is very in focus as well. And that may be distracting to the eye. Now, what's the difference between those two photographs? Well, you can see that he's telling you at the bottom about the aperture, right? So here, the aperture is an f number of f2, whereas here's an f number of f22. Now, remember, the f number is the ratio of your focal length, which in your camera you can't usually change, over the diameter of your lens. So what's going to happen is if you're decreasing your numerical aperture, what you're doing is you're making your lens effectively bigger. So what this guy is doing in this first image is he's taking the picture, but his aperture is exceptionally big, right? Bigger f numbers mean larger apertures, smaller f numbers mean bigger apertures. Bigger f numbers are smaller apertures. So what's going to happen is in the first picture, he's got a really large aperture, which means he's letting in more light that hit the outside part of his lens. In the second picture, what he's doing is he's I'm backwards. God bless. So essentially what he's doing is he's intentionally causing, the left picture is the larger aperture because he's letting in more light from the edge of his lens. And here he's letting in less light from the edge of his lens. So what that's doing is it's causing more spherical aberration for things in the background. This is causing less spherical aberration for things in the background. Blech. You can tell I've never picked up a camera in my life. This is everything I know about photography I knew from freshman physics. But that's the idea. So that's what we mean by spherical aberration. You control that by making your aperture smaller. Now, if you're a photographer, one of the things you have to trade off is that because you're letting in less light when you make your aperture smaller, you also have to increase your shutter time. You have to leave the shutter open for a longer amount of time so that more light can come in and expose your film. And that can be a trade-off. If you're doing like dynamic shots where things are moving around a lot, getting that sort of depth or that large depth of field is difficult because anything moving around and not stationary is going to get blurry. Whereas high-speed photographs tend to have a very narrow depth of field. All right. The last thing I want to talk about is coma. And coma is another kind of aberration. So I can find a good example of coma. No, I don't mean a medical coma.
Oh, okay.
So coma is caused by viewing things that are far from the optical axis of your lens. So normally, like when we're doing ray tracing diagrams, we almost always draw the object so that it's pretty close to the center of your lens. But in the case of coma, you're looking at an object that is somewhere off axis, And what's going to happen is, again, it's going to mess up your angle of incidences and cause asymmetry in the amount of refraction you get, so that you're going to get different focal points sort of spread across some range. Now, what's that going to look like in my photograph? It means that things near the middle of the image are going to be in focus, but things near the edge are going to be distorted. Now, why might I care? Well, sometimes you do it on purpose. A fisheye lens is so named because it's big and bulbous and round, like a fisheye. And what a fisheye lens does is it gets images where you can see a very wide angle worth of stuff. No, I don't want to buy your lens. I just want to look at this image. Show me your fisheye lens picture. There we go. So you can see that what's happening is they've got an image of this thing, but you can see that what's happening is near the edges, the shapes are all distorted. See how all the buildings are curved and weird? Right. It's because they are far from the optical axis and they're being distorted by coma. But the trade-off is that even though the images are distorted, you've got a large angle of view. You can see things from a pretty wide angle, left or right. That's what I mean by coma. It comes from looking at images that are far from your field of view, or far from your optical axis. And the way you adjust that is by adapting the shape of your lens. So very, very complicated lens crafting can go into making coma less of an issue. You'll get a more flat reception across the entire field of view. Woot. Super, super easy. Any questions about that?
Not really.
Yeah. Now, what am I expecting you to know? I'm expecting you to know what these different things are, what they come from, and how to correct for them. If I'm going to ask you questions about them, it's probably going to be in the form of being able to recognize it when you see it, or to talk about how I might cause it or cause it to cease to be created. That's the kind of thing that I'm looking for you to do. Is there math you can do? Not so much, because the math of this stuff is going to be very quickly outside the realm of what we can do without having more complicated mathematics. So I'm not going to make you solve numerical problems, but you should at least be familiar with these kinds of aberration and be able to talk about where they come from, how to make them go away. The last thing we need to talk about is color vision. And color vision is one part biology and one part physics. One thing you probably know is that, the human eye consists of 4 types of photoreceptors. 2 broad categories are your rods and cones. Your rods are photoreceptors that will send a nerve impulse when they're hit by a photon of any light in the visible range. Cones, however, are a different kind of cell, and cones will have a much narrower band over which they will respond. And in general, you've got cones that will respond most strongly for light in the red region of wavelength, one that's largely in the green region of wavelength, and then the third for the shortest bluish wavelengths of vision. So RGB, red, green, blue. Those are the 3 different wavelengths that your eyes will respond to. Now, if you see, say, white light from a light bulb, what's happening is there's light of all different wavelengths coming from that light bulb. And so what's going to happen is when that light hits your eyes, all of your rods, they're going to be stimulated. They're going to send signals because they don't care what wavelength is hitting them as long as it's visible. And all of your cones are going to be also firing because your cones are responding to whichever wavelengths they are set to respond to, and white light has a mix of all of them. And so as a consequence, what's going to happen is if this is your eye and I have, let's say, light in the form of some red, some green, and some blue. If I shine only green light, then what's going to happen is only the green cones respond, and my brain says, aha, I see a green thing. If I shine a bunch of red light, only the red cones respond, and my eye says, aha, I see a red thing. If I have a blue light shining in my face, only the blue cones respond, and I'm like, aha, I see a blue thing. But what's going to happen if I turn on all three? Well, what's going to happen is the photons of light from the red light, they come in and they stimulate the red cones. The green and the blues don't care about those. They don't respond to those at all. The green light comes in and stimulates the blue, or the green cones. The red and the blue don't care about that at all. The blues respond very strongly to the blue cones, but the red and green do nothing. But because I have light of all three wavelengths at the same time, all three of those cells are all responding, and your brain interprets that as white light. So when you're seeing white light, really what you are seeing is wavelengths of light that sufficiently stimulate all three of those bands at the same time. Does that make sense?
Mm-hmm.
Now, if I turn off the green, then what's going to happen is I end up getting red and blue, two of the three types of cones. They tend to respond very, very broadly. And my brain interprets that as magenta. If I do just the green and the blue, well, my brain stimulates two out of the three. The red cones don't do anything. My brain interprets that as cyan. Right. If I do those two, my brain's going to interpret that as yellow, because only the blue cones are standing down. So this is all fine and dandy. And in fact, this actually explains how your television sets work, because your television sets have little pixels, and it only has three kinds of pixels: red, green, and blue. And yet, if they need to show me a yellow object on the screen, all they have to do is turn on the red pixel and the green pixel at the same time while leaving the blue pixel off, and I'm going to see a yellow object. Now, a few years ago, Samsung put out a brand of television set, and they advertised it as having 4 different kinds of pixels. They had a red, a green, a blue, and a yellow pixel. And that yellow pixel actually sent out a wavelength of light that was, honest to God, yellow. Now, this simulation doesn't allow you to turn on a yellow light. But what's happening when I shine a yellow light in my face? Well, it turns out that the wavelength for yellow is longer than the wavelength for red, but shorter than the wavelength for green. And what's going to happen is, even though it doesn't stimulate my red cones as much as actual red light would, it still makes them active. And even though it doesn't stimulate the green cones as actively as actual green light would, it still causes them to light up as well. So even though I'm seeing yellow light, and it's in between what both of the other two types of cones should respond to, they're still both responding. And so my brain is going to react the same way to a beam of actual yellow light that it would to seeing red and green overlapping at the same time. So you cannot tell the difference with the naked eye between an object that is giving off a combination of green and blue light and an object that is honestly yellow, which is why that television set that Samsung created was really stupid, right? They weren't getting anything extra by having that yellow pixel. You couldn't create colors that didn't exist. All you could do was create yellow more easily by turning on one light rather than turning on 2 lights. Notice by changing the mix or the intensity, here I have a high intensity beam of red light and a somewhat lower intensity beam of green light. So what's happening is my red cones are firing to beat the band, and the green cones are firing, but not quite as much. Your brain interprets that particular combination to be orange. But that's what's happening. And by mixing different intensities of each of these three colors, you could, with enough time and practice, create literally any color you can imagine. This is what we call additive color, because you create new colors by adding more photons of a particular wavelength. Super easy?
How do you get black then?
Like that. Black is literally the absence of color. It's the absence of light.
Okay.
Yeah. So that's what it is. If you're, if I'm wearing a black shirt, then what's happening is I'm seeing a lack of reflected light, and my brain interprets that as the color black. So that's the idea. Now, one thing you may have noticed is that when it gets dark, you may have a hard time making out colors. Right? The reason for that is because those cones that are sensitive to particular wavelengths and help you distinguish between different colors, they require a higher intensity of light than the rods do. And so what's happening is when the light starts to get kind of dim, there's not enough intensity around to stimulate the cone cells. So they're not really doing much. You're not getting much information from them as you try to resolve the image. Meanwhile, the rods are perfectly happy. They have a threshold of intensity that is lower than the cones. So even when the light gets dim, the rods are still responding. The problem is that the rods are going to respond regardless of what wavelength is hitting them. So it can't tell you what color it is. You can see the object, you can make out its outline, but you cannot usually distinguish its colors when the light becomes very, very dim. Now, a buddy of mine is colorblind. What's wrong with him?
He can't see certain colors.
Yeah.
Right.
How's that work? What's going on biologically that makes him unable to see colors?
His red cones and like blue cones aren't like the light isn't hitting them, so like the brain itself can't really like tell what color is which, I think, or something like that.
Well, it's not that the light's not hitting them, but what's happening is he's got some sort of mutation, and as a result of that mutation, what's happening is his red cones and his red cones and his green cones, they tend to respond to the same wavelengths as each other. So maybe it's the red cones are responding to too broad a wavelength, so that you hit them with red, they respond, you hit them with green, they respond, but his red cones are going to fire no matter what. And the green cones, not so much. So what's happening is, there are situations where if, I shine this light on myself, my red cones fire and my green ones don't. So I know that that object is red. If I shine this light on myself, my green cones fire, but my red ones don't. So I know that I've just seen an object that's green. But what would happen if this person in the simulation were colorblind is the red cones are going to go off even right now. So this and this are going to look like the same color to that person.
Mm-hmm.
So that's what's happening. And depending on what kind of color blindness you have, it may be total or partial. Most commonly is what they call red-green color blindness, where it's the red and the green cones that are both responding to the same frequencies. So those people could see other colors and discriminate between other colors okay, but red object and green objects in particular, they're going to have a very difficult time with. And they may actually see other colors that look kind of weird because they might involve combinations of red and green in their wavelength profile. Then there are other people who are totally colorblind. Maybe they don't have functioning cones at all, or maybe what cones they have are all the same type. So they simply cannot distinguish between color at all. And they're relying more on their rods for discriminating images than on their cones. So this is, more of a biology thing than it is a physics thing. And it's pretty straightforward. All right, how are we doing? Super easy?
Kinda, yeah.
All right. All I expect you to know about optics. And again, this is mostly qualitative stuff. It's not something that I can do numerical problems with them, but it's certainly stuff you should be familiar with. All right. Well, if that's it, I'm going to let you guys go. See you on Wednesday.
All right.
All right, be safe.
Yeah, you too, guys.
I need you, so I'm gonna,
Okay, what's up?
no, I'm gonna see you in my classroom. Your classroom.
Okay.
Okay, bye.
Yes, ma'am. All right. Have a good one.